Hi folks, this is my second lecture about nuclear chemistry, and we are going to start by talking about the concept of radioactive decay and half-lives and how to do half-life problems. So one thing that is important to know is that you actually already know how to do these problems, because when we studied kinetics, we learned how to do first-order kinetics problems, and first-order kinetics problems are the ones that have got the ln of A equals negative kT plus ln of A0, and this formula here, which tells you the half-life is equal to the ln of 2, which is 0.693 divided by K. And so these two formulas used in conjunction are, this is how you would usually calculate your K and then stick your K in here. And we're going to do a problem like that in a minute. But first, let's talk about the concept of half-lives, which is when you have something that is radioactive, you kind of want to know how long it's going to be radioactive, and that can be described by this beautiful graph here. So this graph is showing, let's say there's some kind of mineral, and that's represented by the black dots. This is a newly formed mineral, which is all radioactive particles of some kind, radioactive atoms of some kind. And they're saying there are 20 radioactive ones and 0 non-radioactive ones in this sample. Now, since this is a radioactive material, it's going to decay over time. And so these little black radioactive guys would change their nucleus and become some other kind of nuclide, and then therefore become non-radioactive. And what this graph is showing is that 100% at the beginning, so at time 0, 100% of your material is radioactive, for example. Then if you wait for one half-life, which is the life that it takes for half of it to decay, and this is a very simple graph, so they've set the half-life equal to 1. So after one half-life, what you end up with is half of these 20 particles will have decayed. So you'll have 10 black particles and 10 red particles. Now this is, I think the hexagon is supposed to represent that it's like a crystal. So this crystal is half as radioactively dangerous as this crystal up here. And you've waited for one half-life, you've gone from 20 to 10. So that's divided the amount of radioactive material by half. So your half-life is that length of time that it took for that to occur. Now what's interesting is that if you wait one more half-life, some people would think, okay, well, 10 of them go away in one half-life, the next 10 will go away in the next half-life. That is not the case with radioactive materials. This is a first-order kinetics type problem, and so it's not that you lose 10 every time, it's that you lose half every time. So you started with 20 and now you're at 10. If you wait one more half-life, you're going to have 5. So half of these 10 black particles will have decayed. So you will only have 5 black particles left. And what you can see over here on the proportion is that you start at 100%, and then you're at 50%, and then you're at 25% here after 2 half-lives. So after one half-life, you're down to 50. After 2 half-lives, you're down to 25%. If you wait another half-life, you get down to 12.5%, and so you've only got 2.5 particles left, which isn't really possible. You can't have half a particle, but typically you're talking about a much larger sample than 20 particles. You'd be talking about a couple of moles of particles. So you get down to 12.5%. You wait one more half-life, you get down to 6.25%, et cetera, et cetera. It's helpful to know that list: 100, 50, 25, 12.5, 6.25, because you run across it, and then the list that matches it is that how much has decayed. So that was how much do you have left: 10, 100%, 50%, 25%, 12.5%. And then the question of how much has decayed is 0%, 50%, 75%, and 87.5%. So that's what this is indicating. So you're waiting one half-life to decay half of it, and then another half-life to decay half of that, and another half-life to decay half of that. And this is something that we studied when we did the kinetics chapter. All right, so Every half-life is the same length, and that's how they can use something called radiocarbon dating to figure out how old something is, how old something that used to be alive is, because all of the living things incorporate carbon into their tissues, and that carbon is originally coming from the atmosphere, from plants and stuff, and it turns out that a small portion of carbon is radioactive carbon, which is carbon-14. So carbon-14, which is a very small fraction of overall carbon, is incorporated at a kind of continuous rate, a constant rate, until you die. And then after you are dead, that carbon-14 is decaying and is no longer being replenished. And so you can watch the percentage of carbon-14 decrease as a dead thing hangs out over time. And so what you can do is take something that used to be alive, like a piece of wood, a piece of leather, some basket made of reeds or something that is an archaeological sample, for example, and you can test how much radioactive carbon is left, compare that to how much radioactive carbon would be in a presently living organism, and say, hey, it's this old. And the way that you do that is you stick your numbers into these two equations. And so let me switch to my black pen screen. All right. You unearth a wooden spear handle and send a sample to measure the proportion of the carbon in the wood that is carbon-14 compared to carbon-12, which is your typical non-radioactive, very stable carbon. The results show that the spear handle has 65% as much carbon-14 as a present-day tree. If the half-life of carbon-14 is 5,730 years, how old is the spear handle? And in fact, that is the half-life of carbon-14. And one thing that's interesting is that in general, after about 10 half-lives, there's not enough radioactive stuff left for you to get a good handle on how old something is. So after about 10 half-lives, which is maybe 50 to 60,000 years, carbon dating doesn't work so hot. There are other radioactive nuclides that you can use that have longer half-lives, and so you can have not radiocarbon dating, but radio other stuff dating. There's something that they'll use cobalt sometimes, and they'll use uranium sometimes. To see how old, for example, rocks are, because rocks wouldn't have carbon-14 incorporated into them over time like organisms do. But you can do this kind of stuff for other radioactive things and do some radioactive dating in that case. So for this, we've got two formulas that we can use, which are the T1 half, and that means the half-life time, is equal to ln of 2 over k, and this is your rate constant, and then your other formula that you end up using is ln of the concentration of E at time t, which means the time that you're interested in. So the concentration of A at whatever time you care about is equal, the ln of that is equal to negative times your negative rate constant times your current time plus the ln of your concentration of A at time 0. So we need to figure out our K, and you do that by sticking in this formula the half-life of carbon, ln of 2, which is 0.693 over K, and then you rearrange and you find that K is equal to 1.21 e to the negative 4 years to the negative first power. So that's your K, and you can go and stick that in there. So what you end up with is negative 1.21 e to the negative 4. And your time is what you're looking for. We're trying to figure out how old it is. So what is the time that it currently is? And then these two, the A0 and the AT, when they give it to you in terms of a percentage, what you can say is that at time 0, what was your percent concentration of A? Well, that was 1. So that was like 100%, whereas right now it's 65% as much, and I shouldn't be doing square brackets. It's ln of 0.65, so that you can say this is 65% of 1. And then you rearrange and do your algebra, and you end up with your time is equal to 3,561 years old. And what this tells you is that that spear handle, when its tree died, that was 3,561 years ago. That doesn't exactly tell you when somebody used that spear. Maybe they used a tree that was dead for a long time before they used it, but that's what that implies. That's the time at which carbon-14 ceased to be incorporated into the wood. And it makes sense if you think about it takes 5,730 years to decay half of it. But what we've got is 3,561 years, and that decayed 35% of it, so you've got 65% as much left. So it's somewhat less than a half-life. So that's pretty good. That is how you do half-life problems. Oh, and multiple choice half-life problems are going to give you easy numbers, and when you've got easy numbers, it's important actually to kind of have that list in your head of amount decayed and amount that's left. This is a sort of important list to have memorized when you're dealing with half-life problems. And this is time. At time 0, none of it has decayed, and 100% of it is left. After 1 half-life, after 1 half-life, 50% of it has decayed and 50% of it is left. After 2 half-lives, 75% of it has decayed and 25% of it is left. After 3 half-lives, it's actually, I should have done this column first. 12.5% of it is left, and 87.5% of it has decayed. After 4 half-lives, 6.25% of it is left, and 93.75% of it has decayed. These numbers come up. If you see a 50, a 75, an 87.5, a 93.75, a 6.25, a 12.5, those numbers will show up in your multiple choice question problems because they're assuming that you will go, oh yeah, that's the number for 3 half-lives. Ha, that's easy. So be familiar and just go, oh, that's one of those numbers. It'll make your multiple choice questions a lot easier. All right. So now we can talk about something called mass defect, and also binding energy, which is kind of cool. All right. In order to see what I'm talking about, let us do these questions here. We've got, how much does an oxygen nucleus weigh? Here we go. It is 2.65535 e to the negative 23 grams. I went and I looked that up. And that an oxygen nucleus is the combination of 8 neutrons and 8 protons. So you figure if you go and add up, if you go and look up the mass of a neutron and the mass of a proton, and you add up 8 of those and 8 of those, you should end up with this number, 2.65535 e to the negative 23 grams. So let's go do that. And so you take this number and multiply it by 8, and you take this number and multiply it by 8. And you add those together. And actually what you end up with is 2.67804 e to the negative 23 grams, which looks pretty similar, but if you look right here, 2.67804 as opposed to 2.65535, there's something wrong. It seems like there's something wrong because it should be the same, right? But what is interesting is that these separated particles have more mass than they do when they are together in a nucleus.
But that makes me very sad inside.
Yes, I understand, Starfish. It makes me sad inside too. the reason for that comes to E equals mc squared, which is when the particles are together in a nucleus, they are more stable, which means that they are lower energy. When the particles are separated and not in a nucleus and just flying around by themselves, they are unstable. They would sort of prefer to be in a nucleus crammed together. So they have higher energy in this state. And the formula E equals mc squared, which is Einstein's famous formula, is telling us that energy is mass. And especially when you get down to a very small particle type level. So these slightly higher energy neutrons and protons are slightly higher mass as well. And the difference between these two, the mass, the observed mass of an oxygen nucleus and the mass that we calculated it really ought to be, the difference between those is the mass defect, which I think is kind of funny and indicates how sad the scientists were to discover this. Like, what? That's defective. How can it be so? The other thing that's interesting about this mass defect and what it implies is that if you are heavier when you're separated and lighter when you're together, if you take these particles and join them together into a nucleus, you lose mass. Mass is going out in the form of energy. And so what this is showing is that you get a lot of energy out of making nuclei. So you can actually get a lot of energy from making a mole of oxygen-16 from its constituent nuclear particles. And so we can actually do this calculation and see that you get a whole bunch of energy from doing this. So the difference, we need to subtract them, is 2.67804 e to the negative 23 minus 2.65535 e to the negative 23. And what you get is 2.269 e to the negative 25, which makes sense because it's 2 decimal places in that you find that difference. So that is the difference between separated and together. And we are going to need to stick this number into E equals mc squared. E equals mc squared requires kilograms, so that's going to be 2.269 e to the negative 28 kilograms. So we stick that in to this. E equals 2.269 e to the negative 28. And then the speed of light is 3e8 meters per second. And then you square that, and you end up with an energy. The reason you need kilograms is because energy is in joules, and joules requires kilograms meters per second squared. So you end up with 2.0421 e to the negative 11 joules. That's for one atom, one nucleus. You need to multiply that by the number of atoms in a mole, so 6.022 e to the 23, and you get the number of joules, 1.23 e to the 13 joules. The number of joules that you would get if you took loose neutrons and protons and crammed them into nuclei and made a mole of oxygen nuclei. And what's interesting is that you know, you look at that number, you're like, okay, whatever, that's some amount of joules. I went and calculated that to kind of give you a reasonable understanding of how much energy that is. That is enough energy to power the electricity for 300 homes for a whole year. So making 1 mole of oxygen would allow you to do that. So that's actually pretty crazy. And what this is basically doing, this is fusion, which is what the sun does. Right? Yes, that's what the sun does. So that is the energy that you would release if you did this. In order to break that shouldn't be the word molecule. In order to break that mole of atoms back up, you would need that amount of energy in order to break it back up, and that's called binding energy. And that's if you take that number and change it to easily readable, that's 12 billion kilojoules of binding energy. That's this amount here. I don't like the term binding energy because it makes it sound like that's the energy that happens when you bind it. This is the amount of energy required to unbind it. So I would prefer that this would be called unbinding energy, because then it would make my brain go backwards. But it's too bad, sorry. What's interesting is this is talking about energy related to fusion, and there's a very nice graph for that. And it is, that's not the graph. This is the graph, up here. You have it on the back of your first page of your notes. This graph here is showing the average binding energy per nucleon, and they've kind of listed the amount of binding energy you get out for each of the nucleons for all of your possible isotopes of things. So all the nuclides are listed here, and this is the amount of energy per nucleon that you would require to unbind it. And the number of nucleons in the nucleus, they have them all in order. So the really small nuclei are over here on the left, and the really big nuclei are over here on the right. So you've got like uranium-238 over here with far on the right-hand side, and hydrogen and helium and stuff are on the left. And what you can see is this nice, really sharp curviness going up here, and it peaks at iron 56, and I'll talk about that in a second, and then it slowly decreases down to uranium here. And what this indicates is that iron 56 would require the most energy per nucleon to break apart. That means that this guy is really, 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 really stable. So up here at the top, they're pretty stable. Down here at the bottom, you've got less stable nuclei, and this is kind of this is an interesting curve, because what it shows is that these guys on the left have a tendency to move towards this peak here. So it's possible to fuse these and get energy out until you reach iron. So all of these nuclides, it's possible to fuse them and gain energy. These, it would require energy input in order to fuse them overall. So you don't really get any fusion past iron 56. But what you do get is, because it's going down, if you can go backwards, you can get energy from fission going to the left from the right-hand side of iron. So that kind of indicates that you're going to be able to fuse these guys, and that's what happens in stars. Hydrogen, helium, lithium, etc. Fusion is possible to occur and get energy out. Whereas these larger guys, it requires an input of energy, and so they're more likely to fizz. You can have fission of these heavier dudes and to gain energy. And as a result of that, what's interesting is that as the star gets older and older and dies, if it runs out of hydrogen fuel, it can use helium fuel. If it runs out of helium fuel, it can use lithium fuel. If it runs out of lithium, it can kind of get desperate and use a little bit of carbon and oxygen. But after that, you're not really getting much out. And when a star gets all the way to iron 56 here, it's kind of toasted and is going to die or go supernova or something. Whereas these guys here, these uranium things, can get formed during a supernova, but you're not, that's not happening in normal star stuff. And so these are the ones that we focus on for our fission reactions for like atomic bombs and nuclear power plants and stuff. And we desperately wish that we would be able to carry out fusion, because if you look, there's much more difference between between hydrogen and iron than there is between uranium and iron. This difference is what you're getting out in a nuclear power plant. This difference is what you're getting out of a sun. So we're really hoping that we're going to be able to figure out fusion, because this curve is much bigger than this curve. All right. So, oh wait, no, I need to be there. I just need to go here. All right, so that's mass defect and binding energy. And then some things, what have humans done with nuclear chemistry? What are some of the things that we've accomplished and learned about? The first one is fission reactors. These are nuclear power plants. And we get uranium-235, and the uranium-235 is unstable and will undergo fission, and you can kind of make that go a lot faster if you are bombarding it with neutrons. And as I talked about before, if you have enough uranium-235, you reach a certain point where the neutrons that come off of a fissioning uranium are the ones that hit the nearby uraniums and cause them to fizz. And so you get a chain reaction. So what's sort of funny about this is that all of this kind of crazy complex chemistry stuff goes on, and it gets really hot. And the heat is what we actually use to make the electricity. We boil water with that heat. And then that steam turns the steam turbine, and from there it's kind of standard electricity generation. If you can get anything to spin, then you can make electricity out of it. But I love that, like, we have all of this kind of top secret complicated uranium fissioning to boil some water. You can slow down the chain reaction if you put in a material that absorbs neutrons without releasing neutrons. So graphite rods have been used in nuclear reactors to absorb neutrons. And water can also be used to absorb neutrons. And if you're absorbing those neutrons, then they're not hitting the neighbor uraniums. And so they don't undergo fission. So one of the structural things of nuclear reactors is that you've got the uranium rods, and they're close enough to each other to have a chain reaction. And then they've got neutron absorbing rods that they'll kind of stick in. And if you stick them in this far, they absorb a little bit. If you stick them in this far, they absorb more. So to make it heat up more, you pull them out. To make it cool down, you push them in. This is the source of the things that go wrong in nuclear power plants, which is if there's something that happens to the system that allows you to slow down the neutrons, then it will heat up so much that it starts to melt everything. And when everything melts, then you can't put your rods in farther. So you've probably heard of Chernobyl, and I'm sure you've heard of Fukushima, because this was only a couple of years ago. Fukushima, the Japanese nuclear power plant that kind of had some trouble when there was a tsunami a few years ago. The tsunami destroyed the power grid nearby in Japan, and normally the electricity is being used by people in Japan, and it wasn't. So that normally would be taking energy away from their nuclear reaction, but it doesn't. And so then it gets hotter, and when it gets hotter and needs to be cooled, then you use the cooling water systems. Well, the cooling water systems have been destroyed by the floods in the basement of the nuclear power plant. And so you've kind of got a couple of things going wrong, which is, it's getting warmer, guys. We need to run our backup systems. Well, our backup systems aren't working because of the floods. Oh, well, guess it's going to get hotter and hotter and hotter, and everything's going to start melting. And, you know, the protection systems and that kind of stuff, when the pieces of those melt, you're like, I guess this isn't working anymore. So that was the problem with Fukushima. Chernobyl, what's fun, the reason I know about this is I went and read the Wikipedia articles about the Chernobyl and the Fukushima events, and they're long and detailed and kind of terrifying and fascinating. So I would recommend that you go read those if you're interested. Chernobyl was like 6 really bad ideas happening all at once. The Chernobyl power plant was scheduled to do a test of a new safety feature. And the safety feature was meant to help during a power outage, which is something that happened in Fukushima. The power outage was sort of a problem. However, the test to see if this new safety feature works was done very poorly, and it was done like during a shift change with a managing guy that didn't really know what he was doing, and shifting to the night shift people that don't really know what they're doing. And so they don't realize until it's too late that the thing that they're doing is causing the neutron absorbing water, which is really important, to boil, which it's not supposed to boil because then it doesn't absorb the neutrons quite as well. And that happened, and also they increased the power output because some other station was down for a little while. So they're doing these two things, increasing the power output and reducing the efficacy of the neutron absorbing water simultaneously. This causes the a steam explosion, and then it actually sets the graphite on fire, which is alarming. And I read a first-hand account of a Russian fireman who got called to the scene. He's alive, he lived, who got called to the scene, and he said that when he drove up in his fire truck and he saw chunks of graphite on fire on the ground outside the Chernobyl station, he knew there was something wrong. And they had just called and said, hey, there's like a fire on the roof or something, can you guys come out? So it was sort of alarming. This steam explosion caused a really big radioactive dust cloud that kind of shot up into the atmosphere and made all of these really radioactive rain clouds that drifted across Europe and raining radioactiveness everywhere. So, Chernobyl. All right. However, that doesn't mean that all nuclear power plants are going to explode. This is actually, they actually have a pretty good safety record. It's just that if there ever is a bad problem, it's sort of alarming. So they are working on safer designs that don't require that are not destroyed by melting. And there's something called a pebble bed reactor that doesn't require lots of equipment to bring the neutron absorbers closer and farther away. So I'm actually sort of hopeful for the future of nuclear power plants. All right. Another thing that you can do with nuclear stuff is atomic bombs. Not you, but countries can do, but maybe they shouldn't. Anyway, it's important to know about the concept of a critical amount, which is, you know, if you have a certain size of uranium, it will be big enough that the chain reaction will be able to continue. If you have a smaller amount of uranium, the neutrons shoot out the edges enough that it doesn't have a chain reaction. So what an atomic bomb does is it takes a critical amount of uranium, chops it in half, and puts the two pieces at two ends of the bomb. And then they drop the bomb, and one of the things that happens in the bomb is that it shoots the two pieces back together into the center. And those two pieces, now that they are together, are a critical amount of uranium. The chain reaction occurs, and it gets really hot and blows up stuff. So, yay, atomic bombs. So that's atomic bombs. Fusion. Fusion, instead of nuclear power plants and atomic bombs, are using uranium-235, which, if you remember, that's fission processes. Fusion is what happens in the sun and in stars in general, and this is taking two hydrogen nuclei and smashing them together to make helium. This gives way more energy than fission, if you remember back up to your nuclear binding energy chart. However, fusion is kind of hard to do because it only works above 40 million Kelvin.
That's really hot.
Yes, it is very hot, starfish. Hey, you're a star. You're very warm. So 40 million Kelvin is really hot. And the reason that it has to be that hot is because to slam those positive charges together, you have to overcome the electrostatic repulsion. So you have to make them go really fast. So that takes a lot of energy. And if you've ever heard of the term cold fusion, this is something that we hope that one day we'll be able to discover. And it's kind of,
wouldn't it be nice if we could have fusion that didn't require 40 million kelvins? Because that's really hot and hard to do.
So there was, back in the 80s, there were a couple of scientists that said, hey, we like got some platinum or something and put it in a jar of water, and then it was amazing because we had fusion. And all of the other scientists were like, that's fascinating, let me try and reproduce your results. And they tried and tried and tried and tried and tried and couldn't reproduce their results. And everyone got so excited about it, and it was all in the news, and the future is now, and we're going to be able to conquer all of our energy problems all at once because of these scientists. And they either messed up really badly or made up a bunch of lies to get famous. And there's still debate about which one it was. But if we ever discover cold fusion, we'll be golden. All right, so that's fusion. And then transuranium elements and particle accelerators. You may have heard of the particle accelerator in Switzerland, which is called the Large Hadron Collider. And they've got particle accelerators kind of around the world, and they're these huge, like, mile round things, kind of underground tunnels, where they can accelerate particles in circles around and around and around and around. And then they finally let them out of the loop so that they smash together. And when they smash together, if you have kind of organized things properly, you can smash together two smaller nuclei, like calcium and berkelium, and you can end up with a larger nucleus if you make them hit hard enough. So this particle accelerator, the most recent nuclide that was made was unun septium, and unun septium, it looks like, was made by smashing together calcium and berkelium, and they made 6 entire atoms of unun septium, which then rapidly decayed to unun septium 294 instead of unun septium 297. And so that's something that they've been doing since the 60s, is shooting particles together and making the new elements. And all of the elements past uranium, I think, have been done this way. I think neptunium is man-made. Come on, internets. The first synthetic transuranium element, yeah, in 1940. That's cool. I didn't know it was that early. Bombarded uranium with neutrons, and it's the first synthetic transuranium element discovered. That's cool. All right. And all of the elements after neptunium have only been observed when they have been made by man in the lab. So, all right. I know what you're wondering. You're wondering, how much will this kill me? All this nuclear stuff. And one of the things that you need to remember is that the alpha, beta, gamma differences in terms of penetration, that is really important as to how much it's going to damage you. The two types of damage that you're worried about are somatic damage and genetic damage. Somatic is the term for cells that are not reproductive cells. So these are your general body cells. This is damage to you. You can end up with radiation burns, and you can end up with damage to your DNA that results in cancer type stuff in you later. So that's somatic damage. That's only going to really happen if you're exposed to large levels of radiation all at once. And genetic damage is something that you would also maybe worry about, which is mutations in your sex cells. So that would cause birth defects or mutations showing up in your offspring. So these are the two things that you sort of wonder about is, well, is it going to burn me to death, and am I going to have mutants for children? And the extent of these two problems is affected by how much energy you got. The gamma radiation is higher energy than beta radiation is higher than energy than alpha radiation. These are really the only three that you worry about when you're dealing with radiation damage. Those are the three kind of common ones. The penetration ability, which we've talked about, gamma radiation can only be stopped completely by 3 meters of lead. Beta radiation can be stopped by 1 centimeter of something, and alpha radiation is basically stopped by anything physical. You can get skin burns from alpha radiation, but that's about it. You can get deeper burns from beta, and gamma just penetrates your whole self. And then the other thing that you worry about with radiation is ionizing ability. Which is the ability of this radiation to rip the electrons off of your molecules, like your proteins and your DNA and stuff. And if you think about alpha radiation is a helium nucleus. If you've got a naked nucleus that is helium, which is a noble gas, that guy is going to be pretty strong at grabbing 2 electrons off of anything that it sees. So while alpha radiation, you can kind of think of it as, oh, it's not that dangerous, it can't penetrate my skin. It does rip your electrons off pretty hard. And so one of the things that you need to be aware of is that you should never eat an alpha producer. Because if you eat it and put it into your system, it can get incorporated into your body. And it can also burn you all the way down your esophagus and rip electrons off of your stomach and rip electrons off of your intestines and stuff as it goes through. Plutonium is known for being an alpha producer. So I know that you guys are really into eating plutonium, but I'm going to recommend that you not do that anymore.
Okay.
And then the other thing that matters is the chemical properties of the elements that you're dealing with that are radioactive. So for example, krypton and silicon. Silicon? Hang on a second. Yeah, it's not silicon. It's strontium. Strontium 90. Strontium, if you look at the periodic table, oops. There we go. Strontium, if you look at the periodic table, is right below calcium, and strontium 90 is a radioactive nuclide that, because it is chemically similar enough to calcium, if it gets into you, your body is like, hey, calcium, and puts it all in your bones. Well, that's not great because it's radioactive, so you have just incorporated a radioactive element into the interior of your body, and it will stay there until it decays. So there's a difference. These are both beta producers, but if you accidentally got beta producing krypton into your body, it just goes straight through. But if you get beta producing strontium into your body, it gets stuck in your bones and stays there permanently, and so your dose of radiation is much higher. All right. You know that I love Xkcd, and this is the Xkcd radiation dose chart. After the Fukushima reaction went downhill, this was one of the comics that he did, and it apparently was well received because a lot of media people used it to explain how much radiation is bad. So here we have the unit that he's using is the sievert, and we've got microsieverts here in blue, and some millisieverts in green. So what we've got is, for example, one little blue square is 0.05 microsieverts. And I love that eating a banana will give you 0.1 microsieverts because bananas contain potassium, and one of the common isotopes of potassium is somewhat radioactive. So watch out for bananas. Getting a dental X-ray gives you 5 microsieverts, and getting just in a day you might get this much radiation. So getting a dental X-ray gives you an extra half day of radiation of your teeth. But you remember that they kind of cover you with all of these lead things to protect you. So because of that and the small amount just on your teeth that they're doing, you don't end up with that much radiation. Um, when you get on an airplane and you fly high up in the atmosphere, you're not being protected from as much of the solar radiation by the atmosphere as you normally are on the ground. And so you end up with about, 4 days of radiation every time you take an airplane flight. And one thing I know is that they've started giving pilots and flight attendants little badges to record how much radiation they're receiving, to kind of monitor that and see whether it builds up and becomes sort of an alarming amount. All right, so all these blue dots, one blue dot is 0.05 microsieverts, whereas a green dot is 20 microsieverts. So that means that there's 400 blue dots in a single green dot. So of these green dots, I'd like to point out, let's see, this one, the EPA yearly limit on radiation exposure to a single member of the public. So this is the amount that it has been decided it's okay to get this much radiation every year. It will be okay if you get that much. Versus that's how much it's all right to get in a year. If you were in the Fukushima exclusion zone for 2 weeks, you would get about a year's worth of radiation. So that is a lot more. And this is, let's see, comparing that to this over here. So that's 2 weeks in the Fukushima exclusion zone, right when it was going off. In 2010, if you went to the Chernobyl plant, if you went there basically now and spent an hour there, you would get 1, 2, 3, you would get much more than you are supposed to get in a year if you spent an hour on Chernobyl. So what you can see is that Chernobyl is much more radioactive now than Fukushima ever was. And that might sound very alarming, like, oh no, I would never go to the Chernobyl power plant, we would all die and turn into mutants. But when you get a CT scan, you get more. Which is why you sort of don't want to get a CT scan unless it's medically necessary. And what is this one? And this amount is the maximum amount that radiation workers, so people that work in nuclear power plants, are allowed to have in a year. So they're allowed to get, like, I don't know, 6 or 7 CT scans in a year, and that's considered to be okay. All right, so green to red, there are 500 green dots and a red dot. And remember that there are 400 blue dots and a green dot. So when you get here, you've got this many red dots, which is how many green dots? 500, 100 millisieverts. Yeah, so this dose here, if you doubled that, this is clearly linked to an increased risk of cancer. So they've got the amount allowed for radiation workers set equal to half of what we know will increase your risk for cancer. So that's not too bad. So that's what, 100 millisieverts. So that's that. But then, let's see, if you get a short amount of time, this much radiation, you will get radiation poisoning. Which makes you feel very sick and you vomit and you can't eat and you've got burns on you and stuff. That's that much radiation, which is 400 millisieverts. That does vary based on your size as well. This is going to be severe radiation poisoning and in some cases fatal. And if you double that, you're pretty much going to die. But you can survive sometimes, and this is definitely die. And I love this, the dose limit for emergency workers in life-saving operations. If you, 250 millisieverts, if those emergency workers are saving people's lives, they're allowed to get somewhat less than radiation poisoning. That's reasonable. And then I love the yellow boxes here. There's 100 red boxes in a yellow box. A yellow box is 1 sievert. If you spent 10 minutes next to the Chernobyl reactor core when it was exploding and melting down, you would have been exposed to 50 sieverts of radiation. So I I thought this was cool. Go read some of the other ones that are kind of interesting that maybe you didn't know you would get radiation from. And that's all I've got. Thanks, folks.